Hello everyone, this is Connor again with the Calc 3 review in preparation for the ASEN 3111 Exam 1. Right now I'm just going to go over a real quick example. I won't be that quick, I'll try to be detailed about this because this is important, but we're going to go over a line integral, right? So I've set up a problem here. We're given this vector field and we're going to integrate along this line that connects the origin to the point 1, 2, -3, right, along a straight line. So in order to do this, the first thing we're going to do is draw a little context. We'll draw out a problem. So what we're doing is we're going from point, well, we'll do some labeling here. We'll say point A to point B, right? A to B, and I'm going to be careful about making that an open curve, right? Because we know that this is not closed. There's no inside and outside. And that's going to be V ds, and I'll be actually a little more, it's a lowercase s because this is a line and not an area. And I know areas are also, they like to use, capital S, right? Not doing that. All right, so when we're attacking these problems, and especially problems where you can't like eyeball it right out of the gate, a lot of times you'll see something where it's like, you have this 2D field, and they give you like, yikes, they give you like for crying out loud, they give you like a square, and they give you a vector field that goes like this, right? And so if you want to add up everything, you just do, it's going to be normal here, and you just add them up here and add them up here, and this side's moving this way and this side's moving this way, so this isn't this ends up being, it's negative over here and it's positive over here, so the whole thing ends up being zilch, right? This is a more complicated example, and the reason I'm doing that is because sometimes you see complicated examples and you'd like to know how to solve them, or remember how to solve them, right? Because you took Calc 3 a few years ago, or maybe last year, and it's been a while, right? So how we usually attack these is, especially if we have, this is not the most perfect line. It's a really nice straight line. It's not perfect. We have this kind of ugly function up here, right? And what we usually do is we parameterize, and we move away from moving in the x, y, and z direction to moving in the t direction. T is not necessarily time, but it's a nice dummy variable that we can integrate over, right? So instead of integrating from a to b, we integrate from t equals 0 to 1, right? Something dt, right? So how we do this, right? We still have to maintain this kind of, this is like the direction of the curve, right? And this is the field we're evaluating along, right? So what we can do is we can first say, and I'm going to erase this just for a little bit. We can first say that we have some curve that we're going to parameterize the curve in terms of t. So we'll call it r. Say r is a function of t. We'll make it real simple, right? We're just going from 0 to 1. That way, we, when we take the integral and we evaluated 0 and 1, it makes our life a lot easier, right? So we can go from, we can just say this is 1 t I hat minus 2, plus 2 t j hat minus 3 t k hat, right? And we know this progresses linearly for each one of these variables from 0 to 1, right? So that's our good r of t. Next thing we want is we want to make sure we're evaluating our vector field along r of t. So we'll say something like we have v of r of t, and this is how we parameterize our x, y, and z in the velocity field in terms of t, right? So we have like our x. We have our x, y, and z this is like the translation between our t and our xyz space, right? That's how we define it. So we can evaluate this. We can say this is v of r of t, and this is just equal to x of t, y of at t, right? That's how our line is moving. We have x at t, y at t, z at t. That's how this is progressing, right? And so once we have that, we can say, okay, so we're evaluating our vector field along this curve, right? We still need the direction of the curve, right? And we know we can find the direction of any curve. We can see how it's changing with respect to some variable if we take the derivative of it, right? And specifically, if we only want the direction, we're going to find the derivative and then divide by the norm of that derivative so that we end up with a unit length vector, right? So I'll take this down here. We'll say r prime of t, right? Differentiating. We'll say r prime of t is equal to, and this is pretty simple, just taking with respect to t, we're going to say this is 1 I hat plus 2 j hat minus 3 k hat. All right, and then we'll normalize. We know that the norm of r prime of t, and I better be good about my vector notation. This is the square root of 1 squared plus 2 squared plus 3 squared. That is 1 plus 4 plus 9. That is a square root of 13. And we'll leave it at that for now. We can plug and chug later, but what we can do is we can say this is r hat prime of t is equal to this divided by this, right? And so we end up with 1 over root 13 I hat plus 2 over root 13 j hat minus 3 over root 13 k hat, right? So now we have like our direction. This is how we define, like, okay, are we moving, oh, my colors got messed up. That's very sad. Are we moving in the direction, is our velocity field moving in the direction of the curve, right? So we'll continue along. We can put all this together. We got this, we got our velocity field, we've got our direction. We look back up here, that's kind of all we need, right? So we'll say we're integrating now from 0 to 1 of v of r of t times the direction, or times dotted with the direction. We want that agreement between them, r prime of t. All right, so, and then with respect to dt. All right, so with this, we can start plugging and chugging. So if I plug in for x squared, y, and z, wow, that's going to be a lot. Well, actually, no, it'll be fine, right? So we'll plug in for the x, y, and z components of the velocity with these r components right here, our x at t, y at t, and z at t. And I'm going to take a quick cut and just evaluate those real quick, but we can regroup in just a few seconds. All right. All right, I'm done evaluating. So if you're not ready for that yet, go ahead. This is your chance to take a pause because I'm about to show the answer. I know you don't want to be spoiled, right? So here I have it right over here. So essentially what I did is I just took my x at t, y at t, and z at t, and I plugged it all in up here. And I see I have 8x squared, so that got a t squared right here, and then y times z, 2t times negative 3t. Put it all together, and good God almighty, look at me go. That is the second mistake I've caught. Luckily, we haven't integrated yet. And the other mistake I caught is that 1 plus 2, or 1 plus 4 plus 9 is 14 and not 13, right? So I corrected that. Make sure you did that too. But yeah, I pulled these x, y, and z components in for everything in my v function, right? And I evaluated it, and I get this guy right here, right? And so then what I do is I keep moving forward with this integral, and I dot it with the direction, right? So when we do that, we end up with this guy, and I tell you what, we are 99% of the way here, because now we just have to integrate a polynomial, right? So we can walk through this together. This is going to be negative 1/5, 48 over root 14 t to the 5th plus 1/3, 24 over root 14 t cubed minus 1/2, 30 over root 14 t squared. Evaluated 0 to 1. Aren't you glad we just did that one little 0 there, right? So now we're going to evaluate all this and essentially just adding all these together, right? Because we're going to positive 1. And we have all this added together. And we do that, we get, give me just a second to find it. Looks like I got negative 83 fifths. Sorry, 83 over 5 root 14. Let me make that way prettier. Negative 83 over 5 root 14, which is equal to negative 4.44. All right, so quick, we'll go back over how we did this. So we established that we had some velocity field, right? We have our field, we have the direction of the curve we're integrating along. We parameterize this in terms of x of t I hat plus y of t j hat plus z of t k hat, right? We put it all in. We're evaluating along that curve, you know, at every point. So I'll draw a picture again. So if I have just some arbitrary curve that I'm going along and I have some, you know, vector field in there along with it, right? We're essentially, we'll zoom in a little bit. You know, if we look at one point right here, one infinitesimal point, we're evaluating our vector field at that point, v at x, y, z, right? And we're seeing how much it agrees with our direction at that same point, r prime. And we're being specific about unit vectors, unit length, and we dot these together. So v dot r prime evaluated r of t, and we just integrate all over t, right? So you can see how we went through this. We got the direction, we took the norm of it, we corrected it because it was 14 and not 13. Ha 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 ha. Dotted them together, and then once we had that, sorry, not quite right yet. Here we dotted them together, and then we just plugged it in the interval, right? And it was a very simple polynomial integral. We evaluated it at 1 and then subtracted 0, right? And that was really nice, and this is the answer we got, right? So that's our example with the line integral. If you have any concerns about this, if you think I did it wrong, please let me know. Wow, wouldn't that be embarrassing? And then if you had any other questions or comments about the video, please come talk to us in office hours. We have our schedule up on the Engineering Fellows website under the aerospace calendar. We'll be in the Aero building on Tuesdays and Thursdays. Otherwise, you can reach us by email. That email is in the description. Leave a comment. Get a hold of us however you can if you want to talk about your curriculum, what you want to do in your life, stuff like that. We've had those same questions when we were where you are, and we love to help you get through it. All right, so thanks for listening. Good luck on your exam, and good night.